In May of 2025, a physicist at the University of Portsmouth published a peer-reviewed paper in the journal Physical Review D, arguing that the Big Bang was not the beginning of everything. According to his calculations, our entire observable universe, every galaxy, every star, every atom in your body, may sit inside the interior of a black hole that formed inside another larger universe. This is not science fiction. It is not a thought experiment. It is mathematics published in one of the most rigorous physics journals in the world by a serious cosmologist with a falsifiable prediction attached to it. His name is Enrique Gaztañaga, and the paper is titled Gravitational Bounce from the Quantum Exclusion Principle. To understand why a respectable physicist would make such a strange claim, you have to first understand what is wrong with the story most of us were taught in school. The standard model of cosmology says that everything began roughly 13.8 billion years ago in something called a singularity, a point of infinite density, where the laws of physics simply break down. That phrase, where the laws of physics break down, sounds like a small technical detail. It is not. It is an admission that at the very beginning, our best theories give us no answer at all. As Gaztañaga himself put it, the Big Bang model begins with a point of infinite density, where the laws of physics break down. And this is a deep theoretical problem that suggests the beginning of the universe is not fully understood. So Gaztañaga and his colleagues did something unusual. Rather than starting with an expanding universe and trying to work backwards to figure out how it began, they reversed the question. They asked what happens when an enormous, dense cloud of matter collapses inward under its own gravity, the way a dying star does when it forms a black hole. The classical answer, going back to the work of Roger Penrose in 1965 and later extended by Stephen Hawking, is that such a collapse must end in a singularity. The matter falls inward, the density rises without limit, and physics surrenders. But Gaztañaga's team added something the classical picture leaves out, which is quantum mechanics. There is a rule in quantum physics called the exclusion principle. In simple terms, it says that two identical particles cannot occupy the same state in the same place at the same time. It is the reason ordinary matter is solid. It is the reason a white dwarf star can hold itself up against its own gravity instead of collapsing. And in Gaztañaga's calculations, when you apply this rule to matter falling into a black hole, the collapse cannot continue forever. The particles refuse to be crushed any closer. The infall slows. It halts. And then it bounces. What emerges on the other side of that bounce, according to the maths, is a region of expanding space and time that looks remarkably like our own universe. The rebound naturally produces a phase of accelerated expansion, which is what cosmologists today call inflation, and a slower acceleration that continues into the present, which is what cosmologists call dark energy. The model does not need to invent a separate inflation field. It does not need to invent a separate dark energy. Both effects fall out of the geometry of the bounce itself. Gaztañaga summarized it this way. One reason this model is compelling is its simplicity. It explains cosmic expansion, inflation, and dark energy using only gravity and quantum mechanics, with no extra assumptions or unknown ingredients. If the model is correct, then the implication is staggering, and it is also quietly humbling. In Gaztañaga's own words, in this framework, our entire observable universe lies inside the interior of a black hole formed in some larger parent universe. He went further. He compared it to a nested structure, black holes inside black holes like Russian dolls. And he made a careful point. Not every black hole would have a habitable universe inside it. The size matters. Large black holes allow time for galaxies, stars, and planets to form. Small ones produce universes that expand or collapse too quickly for anything interesting to happen. If we exist, he reasoned, we must by necessity exist inside one of the rare large ones, because that is the only kind in which observers like us could be possible. This is the part that makes the idea different from pure speculation. The model has a prediction. If our universe really did emerge from a bounce inside a parent black hole, then space itself should have a slight curvature. It should not be perfectly flat as the standard model assumes, but very gently closed like the surface of a sphere. The number Gaztañaga and his team calculated for this curvature is approximately negative 0.07, give or take 0.02. That is small, but it is not unmeasurable. The European Space Agency's Euclid spacecraft, currently in flight, is producing the most accurate measurement of cosmic curvature ever taken. Its full results are not expected until around 2030. So somewhere in the next few years, we may have an actual yes or no answer to the question of whether the universe is inside a black hole. That is not a sentence anyone has been able to say honestly before. This idea, by the way, is not as new as it sounds. It was first proposed in 1972 by a theoretical physicist named Rajkumar Pathria in a paper published in the journal Nature. Pathria noticed something curious. The radius of the observable universe is approximately equal to the Schwarzschild radius of the universe's total mass. The Schwarzschild radius is the precise distance that defines the boundary of a black hole. In other words, if you took all the matter in the observable universe and asked how big a black hole that much mass would create, the answer is, roughly, the size of the observable universe itself. Pathria thought that was too strange to be a coincidence. For decades, almost no one took him seriously. 20 years later, the physicist Lee Smolin published a book called The Life of the Cosmos, in which he argued that every black hole creates a new universe inside it, and that small variations between these child universes might function like Darwinian natural selection, slowly producing universes capable of forming stars, planets, and eventually life. Smolin called the idea cosmological natural selection. For most of the last 50 years, these ideas lived at the edges of mainstream physics. What changed is the data. In February of 2025, a researcher named Lior Shamir at Kansas State University published a paper in Monthly Notices of the Royal Astronomical Society, one of the oldest astronomy journals in the world. He had taken images from the James Webb Space Telescope's deepest survey of the early universe, called the JWST Advanced Deep Extragalactic Survey, and he had measured the direction in which the spiral galaxies in those images were rotating. He looked at 263 galaxies. In a uniform, well-behaved universe, you would expect about half of them to spin one way and about half to spin the other. That is not what he found. 158 of them rotated clockwise. Only 105 rotated counterclockwise. Roughly 2/3 spun in the same direction. The asymmetry is so clean that, as Shamir put it, the analysis was done by quantitative analysis of their shapes, but the difference is so obvious that any person looking at the image can see it. Shamir himself offered two possible explanations, and a careful viewer should hear both. The first is the dramatic one. The universe was born rotating. And if the universe was born rotating, that lines up neatly with the theory that our entire cosmos is the spinning interior of a black hole, because black holes themselves rotate. If we are inside one, we should expect to see its spin reflected in the largest structures around us. The second explanation is more mundane, but also more important. The Milky Way itself is rotating, and the Earth moves with it. Because of the Doppler shift, light from galaxies that spin opposite to our own motion may appear slightly brighter than light from galaxies spinning the same way as us. If that is the cause, then the asymmetry is not about the universe at all. It is about us, looking out from the inside of a moving galaxy and mistaking our own motion for a property of the cosmos. Shamir is honest that we do not yet know which explanation is right, and a separate piece in Scientific American, published in April of 2025, pushed back hard, arguing that earlier and larger galaxy surveys have not consistently shown the same effect. So we should take it as a clue, not as proof. Around the same time, in March of 2025, two physicists, Stefan Gielen at the University of Sheffield and Lucia Menendez-Pidal at Complutense University of Madrid, published a paper in Physical Review Letters with the technical title Black Hole Singularity Resolution in Unimodular Gravity from Unitarity. In plain language, they showed mathematically that if you apply quantum mechanics to the center of a black hole, the singularity does not have to be the end of space and time. Instead, it can be a transition, a region of large quantum fluctuations from which space and time emerge again on the other side, in a structure called a white hole. A white hole is the time-reversed image of a black hole. Where a black hole pulls everything in, a white hole pushes everything out. If their model is right, then the center of every black hole could be where a new region of time begins. As Gielan put it, in quantum mechanics, time as we understand it cannot end as systems perpetually change and evolve. Notice how this dovetails with Gaztañaga's work. One paper says that black holes can give birth to new expanding regions of spacetime. The other paper says that those new regions look like our universe. There is more. In March of 2025, the international collaboration, running the Dark Energy Spectroscopic Instrument in Arizona, a project involving more than 900 scientists from over 70 institutions, released its second major dataset. They had measured the positions of nearly 15 million galaxies and quasars, building the largest three-dimensional map of the universe ever made. And they had used it to track the influence of dark energy across the past 11 billion years of cosmic history. The result, when combined with other measurements, was a statistical preference for the conclusion that dark energy is not a constant after all. It seems to be weakening over time. The strength of the evidence sits between 2.8 and 4.2 sigma, depending on which supernova data is used. That is not yet the 5 sigma threshold physicists usually require for a discovery, but it is the strongest hint in years that the standard model of cosmology may be incomplete. Meanwhile, the rate at which the universe is expanding, a number called the Hubble constant, is in the middle of its own quiet crisis. Measured from the local universe using nearby supernovae, the value comes out around 73 kilometers per second per megaparsec. Measured from the cosmic microwave background, the leftover light from the early universe, the value comes out around 67. These are not the same number, and after years of careful work, the gap between them has not closed. In January of 2025, a team led by Daniel Skolnick at Duke University reported a value of 76.5, which makes the disagreement worse. In May of the same year, a team led by Wendy Friedman at the University of Chicago, using the James Webb Space Telescope, reported 70.4, which makes it slightly better. In December, the final dataset from the Atacama Cosmology Telescope confirmed that the disagreement persists. Even the basic question of how fast our universe is expanding does not currently have a single agreed answer. That is the climate in which the more radical ideas are being taken seriously. Cosmology is not in a comfortable place. The standard model is not broken, but it is bending in several directions at once. And then there is the question of what reality is made of at the smallest scales. In December of 2024, Google published a paper in the journal Nature describing a new quantum chip called Willow. In a benchmark calculation, Willow performed in under 5 minutes a task that, according to Google's own analysis, would have taken the world's fastest classical supercomputer approximately 10 septillion years. That is a number so large it exceeds the age of the universe many times over. Hartmut Neven, the founder of Google's Quantum Artificial Intelligence Lab, made a public claim about what this meant. He said the result lends credence to the notion that quantum computation occurs in many parallel universes, in line with the idea that we live in a multiverse, a prediction first made by the physicist David Deutsch. Deutsch has argued for decades that the only intuitive way to explain why a quantum computer is so much faster than a classical one is that the computation is being carried out in many universes at once. The interpretation Neven was invoking has a longer history. It is called the many worlds interpretation, first proposed in 1957 by a young physicist named Hugh Everett, and later popularized in the 1970s by Bryce DeWitt. Not everyone agreed with Neven's claim. The astrophysicist Ethan Siegel publicly responded that Neven had conflated a mathematical structure called a Hilbert space, which is where quantum wave functions are described, with the idea of a physical multiverse, and that the speed of the Willow chip can be explained perfectly well within other interpretations of quantum mechanics that involve only one universe. Both views are held by serious physicists. What everyone agrees on is the result. The chip did the calculation. The disagreement is about what the calculation means. So step back for a moment and look at the pattern. A peer-reviewed model says our universe could be the inside of a black hole. A peer-reviewed analysis of the most distant galaxies ever imaged finds that they are not rotating randomly. A peer-reviewed paper on quantum gravity says black holes can give birth to new expanding regions of space-time. The largest map of the universe ever made suggests dark energy is changing in ways the standard model cannot explain. The expansion rate of the universe gives different answers depending on how you measure it. And the most powerful quantum computer ever built is producing results that one of its lead scientists openly interprets as evidence of parallel realities. None of these findings taken alone is enough to overturn the way we understand the cosmos, but they are not isolated. They all point, in their different ways, in the same direction. They point to the possibility that the universe we live in is stranger, more layered, and more deeply connected to other things than the textbooks suggest. This is where it is important to be honest. None of this is settled. The black hole universe model is a mathematical proposal, not a confirmed discovery. Its testable prediction, the slight curvature of space, will not be measured precisely until the European Space Agency's Euclid mission completes its work around 2030. The galaxy rotation result could turn out to be an observational bias caused by our own motion through the Milky Way, rather than a real property of the cosmos. The DESI dark energy result is below the threshold physicists require to call something a discovery. String theory, which provides one of the mathematical frameworks used in some of these arguments, has not yet produced a single experimentally confirmed prediction in over 40 years, and serious physicists, including Peter Woit at Columbia and Carlo Rovelli, have publicly argued that it is a failed framework. The simulation hypothesis remains philosophical. The many worlds interpretation remains an interpretation. We are not at the end of the story. We are somewhere near the middle of a chapter that has not yet been finished. What we can say with confidence is this: the idea that our universe sits inside a black hole, once dismissed as fringe, is now the subject of a peer-reviewed paper in one of the most respected physics journals in the world, with a falsifiable prediction attached to it. The data coming back from the James Webb Space Telescope is not behaving the way the standard model said it would. The expansion rate of the universe has not been pinned down. The smallest pieces of reality, the ones that quantum computers exploit, are doing things that some of the people who built those computers believe can only be explained by other universes existing alongside our own. We are living through a period in cosmology where the questions are getting larger, not smaller, and where the answers, when they come, will almost certainly require us to revise things we thought we already knew. If there is anything to take away from this, it is not certainty. It is the opposite. It is the recognition that the universe is still hiding most of itself from us, that the people most qualified to study it are openly disagreeing about its basic nature, and that some of the strangest ideas in modern physics are no longer the ones living in popular books or science fiction novels, but the ones being written into peer-reviewed journals by professors at real universities, with real predictions, waiting for real telescopes to deliver an answer. We may, in the end, find out that the universe is exactly what the standard model says it is. Or we may find out sometime in the next decade that we have been living inside something else all along, and that the boundary we cannot cross is not the edge of space, but the inside of a black hole that exists in a universe we will never see. Either result would be one of the most important things the human species has ever learned. Either result would change what it means to look up at the night sky. And either result, when it arrives, will be the work of people who were patient enough to keep doing the maths, keep building the telescopes, and keep asking the question, even when the answer was nowhere in sight.